end the suspense for non-English, non-native English speakers. There's a saying in English that imitation is the sincerest form of flattery. So it's imitation that we're going to be talking about today.
Do you mean imitation or stealing?
Well, yeah, but what they say about, what did Picasso say?
Great artist.
Good artists borrow, great artists steal.
Steal, absolutely.
Okay, I'm Maurice Naftalin, and I put these things up to satisfy my insecurity and kind of reassure me that I really should be talking to you. A couple of books and some community memberships, Java Champion and so on. And as of 10 minutes ago, I'm happy to announce I'm now a developer and technology evangelist for CDG Group. So I have a job, first time in 25 years.
Oh, congratulations, Maurice. I'm very happy for you.
I'm not sure how I'm going to take to the discipline.
Does CDG mean Charles de Gaulle?
To you, maybe.
All right. And my name is Jose. I'm also a Java champion, just as you are, and also Java rockstar, which is a lost title, in fact, because those were the days of Java 1, and there's no more Java 1. It has been replaced by Oracle Code 1. And I just put here a set of links if you're interested in some Java technical content and stuff. There's a YouTube channel here with some hopefully interesting content, and also some GitHub rubbish put on a repository that you can download and clone. Some people do that sometimes. And different things. And that's it. And of course, the slides of this presentation will be published by the conference, and we also put them usually on some SlideShare accounts. So you have a link to this SlideShare account there. And you have something more to tell us.
I do have something more. I've got yet another announcement. So this announcement is about Edinburgh and JALBA, which is an unconference. For people who aren't familiar with the idea of an unconference, it's a place like a conference except without set timetable and prepared talks. It's where people come together and organize themselves. And what happens in an unconference is the part that many people think is the most important part of conferences like this, which are the hallway conversations. So it's hallway conversations and outings. It's a family-friendly event. You may have heard of JCrete. It's kind of modeled on JCrete, but it's because it's in Edinburgh, it's different. It'll be running this year for the third time, from the 7th to the 9th of May. And if you want to get into it, then the thing to do is to go to jalba.scot and pre-register there. Okay, I think that's probably enough announcements.
Okay.
Right. So, what's this talk about? It's about functional programming and the influence that it's had on object-oriented programming. So, functional programming has been admired for a long time by theorists in the programming community. I've been around functional programmers for ages, and they're always very, very smug about what they do, because they think that their discipline is elegant and mathematically sound. The various features make functional programs really, really nice to work with. Higher order functions, which have been around really since the beginning of programming, parametric polymorphism, which we know of as generics, and pattern matching. All of these things have been a set part of functional programming for decades. Often it's not practicable because it tends to deal with immutability. You get an awful lot of structure copying. And so the result of that is that functional programming has not been entirely an academic pursuit, but it's stayed on the margins of mainstream programming. Object-oriented languages, by contrast, have been really successful since the 1980s. They've had some great things about them. Subtype polymorphism, which we know as inheritance. Strong static typing, that Java definitely has always had. Automatic memory management, which has been a huge boon to programmers, well, to non-functional programmers. Functional programmers get it for free, but it's very, very expensive. So it's like free but expensive. They don't have to work on it, but the result is their programs are very memory hungry. So object-oriented languages have been very successful, but they've always suffered from feature envy, because the mathematical elegance of some of the aspects of functional programming have just always been something we've wanted. Here we are.
Maybe I should.
So, how have the features from functional programming come into our world? The starting point really was the pizza paper. In 1997, I think, Phil Wadler, a friend of mine in Edinburgh, heard from one of his students that there was this whizzy new language called Java, which was really taking over. He's a functional programmer from way back. He's a very big name, one of the designers of Haskell. And his student told him, you should get in on this. And so he got together with Martin Odersky, and they wrote the pizza paper. They wrote the paper, as you can see, called Pizza into Java. And there's nothing behind the name. They just wanted something food-related. And they took 3 features, the ones that were on the previous slide, generics, higher-order functions, and pattern matching, to see how could they fit these into an object-oriented framework, and particularly Java. So this paper itself didn't go anywhere much, but it was foundational because they went on to produce something called generic Java, and this was a collaboration with Sun Microsystems because Sun was interested in the ideas in pizza, and Martin and Phil got together with Gilad Bracha and David Stoutermeyer, and with generic Java, they thought very specifically about how they could implement those features in Java. And the result of that was eventually that, well, straight away, we're going to describe how that was quite a difficult process. Generic Java had to make a lot of compromises. We'll talk about those because they're very relevant to Java programmers. They're why things are the way they are now. And Martin Odersky was frustrated enough about this to go off and write and invent Scala, and we'll talk about that as well. Gilad Bracha, who was working for Sun Microsystems, went on with the help of Odersky and Wadler in the expert group to create generics, which eventually got into Java generics, which eventually got into Java in 2004. So generic Java was like an intermediate stage, and we'll take a look at that. So Java took 3 courses to eat the pizza. We got generics in 2004. After a long delay, you'll see there's 6 years between generic Java and Java 5. Higher order functions didn't arrive until Java 8 in 2014, and pattern matching is real soon now, right?
Well, it's not completely soon, but it's definitely under work currently. Under the umbrella of the so-called Amber project. Maybe some of you have heard of that. And this is something that is going to come to be made available in the Java language in the next few years, we could say.
Yeah.
Piece by piece, just like a pizza, right?
Yeah.
The first piece should be available. We're going to talk more about that in the following, as the record project that should be made available as a preview feature in Java 14, released in March. And we should have the early access versions quite soon now.
Jose doesn't know the American idiom, real soon now, which means almost never. But we are more hopeful than that for pattern matching in Java. Scala, by contrast, didn't have... we're going to describe why it was so hard, or at least in one case, why Java has been so slow in adopting the ideas in pizza. Scala didn't have the basic problem as backward compatibility. Java's always been really determined to maintain backward compatibility, and that has really pushed these features sometimes a long way out of shape. Scala didn't have these problems. That's why Odersky went off and started again from scratch to avoid those constraints. And so Scala was able to absorb all these features in one go, and was up and running in 2004. Okay, so we're going to look at each one of these features in a bit more detail now to try to understand why they are the way they are in the different languages. Part 1, generics. So we've got the three things: generics, enclosures, and pattern matching. So the problem with the biggest problems were faced with generics. They faced 2 big problems in introducing generics into Java in 1996, and they are still problems that continue now. Well, what you want to write when you want to create at runtime, you want to create, if you've got a list of integer and you want to create an array of integer out of that list of integer, you would love to be able to write what's in the top box there. But you can't do it. what you have to write is what's in the bottom box. Why is that? The answer is because you have to have some way, when you construct an array, you have to have some way of telling the array what its runtime type is going to be. And there are no runtime types. There never have been runtime types in the Java virtual machine. And one of the conditions of adopting generics in Java, in Java 5 eventually, was that they weren't going to change the virtual machine to hold runtime types. So when you create a new integer array in the bottom code there, you're creating the class information at runtime that's going to be needed to make the new array, and that's quite frustrating. And the presence of runtime type information leads to a lot of problems, like you can't create an instance of, you can't do an instance of test, and you can't create various other things as well. We'll come to some of them. So the second problem, that's the first problem, was no runtime type information. And the second problem was the way that they'd implemented array subtyping from JDK 1 onwards. And you can write the code that's in the top box, so that's in the box here. That code says, because int is an array of integer, and an array of integer is a subtype of array of number, you can write the second line of that. You can say a number array is going to be assigned an integer array.
But what would happen if I want to add, let's say, a float through this numbers pointer?
Well, we'll see that in a moment. First of all, let me say, this is the important term here is covariance. And what that means is, if integer is a subtype of number, then an integer array is a subtype of a number array. And they adopted covariance for arrays. And the reason that they did that was so that they could have generic methods. Because what kind of a language is it in which you can't write a library method which will sort an array of anything? If you want to be able to sort an array of anything, then you're going to have to define it on object. You're going to have to define that sort method on an object array. And therefore, integer array has to be a subtype of that, and so does every other reference type that's going to be sortable. And that's why they had to have covariance. What was your question?
My question is that since I have 2 pointers of different types, the first one is a type array of number, and the second is array of integer. So if I take those 2 pointers pointing to the same place in memory, it should mean that I should be able to put floats in an array of integers.
Unfortunately,
through the number array pointer.
Unfortunately, you really can try to do that. You can write the code that's in the box there. If numbers is an array of number, then you can write number 0 equals 3.14, which is actually a double. Mm-hmm. And this is bad news, because arrays know what their type is. And even though this has a static type, the variable numbers has a static type of numbers array, it actually knows that it's an integer array, because from the earlier example, you saw that an array knows its type at runtime. It's the one thing that does carry runtime type information. So it's an exception. And you've turned what should be a compile time error into a runtime exception. This is really a problem. It's not a problem most people come across with arrays most of the time because it's a bit obscure, but they couldn't carry that forward into all the collections classes when they generified things. And so the lesson to take away from this is that covariance is only good for getting things out of a container. If you start putting things into a container because when you take things out of a container, you know what they're a subtype of. But when you try to put things into a container, it doesn't work. So that's the second problem. They got around the first problem. They've never got around the second problem, I should say. Right? So that problem with arrays is still there. They got around the first problem, the lack of runtime type information, by using something called type erasure. And the idea of that was, we'll do all the type checking. We'll make sure that your program is strongly typed correctly at compile time, and then we're going to throw away all the type information. And so at runtime, every generified method and class is going to be compatible with the non-generified one. And the reason for that was, I mean, the strong reason for doing that was you wouldn't have to have two versions of the libraries. The migration path was relatively easy. You could generify your library classes before your client code, or your client code before your library classes, and this scheme ensured compatibility regardless. So this was actually really important for getting generics into the language. Without it, there wouldn't have been a migration path. And without a migration path, Java wouldn't have had generics, or it wouldn't have survived.
Absolutely. And so you know that the type erasure in generic Java is about removing this type T from this example, for instance, there, this older class that is parameterized by the T type. And in fact, if you look at the class file itself, the T type is gone. All you have in the class file is an older class that can hold objects. This is what type erasure is about. And the countermeasure would be reified generics, which is not something we have in Java. So the problem is, how does it work? Because, for instance, when I write this kind of code, I create this order of string, right? And I'm not going to be able to put a number is this order of string. If I call order set and pass a number, for instance, as a parameter, I will have an error at compile time. The compiler knows that this is going to be wrong. And this is exactly the behavior I want to have, because I want to be able to say that, yes, this is an order of string, despite the fact that the JVM or the class file doesn't know about it. So how this is done? Well, this is all handled by the compiler. The compiler just checks the type by putting the cast in the right places in the class file, and just by making things work for me as a code writer. And the same goes when I want to put out an object from my get method. If I call order.get, I do not need to cast this object, because the compiler knows that this is a string of character and will do the cast for me. Because in fact, what I really get from this get method is an object. It is not a string of character.
So when you see these casts like this, your hackles immediately rise. You feel, wow.
Yeah, absolutely.
So how do I know this is going to be right? I mean, could I get a class cast exception from this?
Well, if I'm using this order through the row type without putting the typed information with it, well, yes, I will have a class cast exception in some cases.
But only though, if you ignore the warnings.
Absolutely.
The unchecked warnings. They're only warnings, right? So you can safely ignore them.
Well, we can suppress the warning.
You can suppress the warnings.
We all do that.
Yeah, of course we do. The pizza paper had what it called, I'm sorry, I apologize on their behalf, a cast iron guarantee. And the cast iron guarantee was, if at compile time the types have all checked out, then a cast that's inserted by the compiler will never fail at runtime.
Absolutely. But there's more, because in object-oriented programming we have inheritance, right? And inheritance brings another range of problems with this kind of type erasure stuff, and another row of problems that will bring more hacks to the class file to fix them. Let us see just one of them, one small of them. Suppose we have a string order class that extends the order of string. And of course, in my string order class, what I want to do is override. So this is object-oriented programming, override this set method that takes a string as a parameter. Now, the problem is that in this order string object that I'm inheriting, I do not have a set string method, I have a set object method. So this set string method is not going to override the set object method because they don't have the same signature, which may be an issue. So guess what? There is a...
I think a hack will work.
Yes, there's a secret hack, in fact, in a class file.
Don't they always say every problem in computing can always be solved by one extra level of indirection?
Absolutely.
Here we go.
Which is a polite way of saying one more hack.
Yeah, right.
Right. So if I check the class file, and this is very easily done, there are plugins in every kind of IDE to do that, you will see that, yes, there is this set string method, but then there is another method that has been added, which is the set object method, which is just there to override the set object method from the older class. And it's not a real method. Well, it is a real method, but it is a synthetic method. And you cannot create synthetic method by yourself. Synthetic is not a keyword from the Java language. So you cannot put that kind of keyword in your .java source file, of course. This method is only created by the compiler. And by the way, if you check the class that is called class, you have, the method, you have a is synthetic property on this, which will tell you that this method is indeed synthetic. So what happens if, suppose you have a method that gets an order of string as a parameter. So you get that pointer, order of string, and they say we are just compiling the code. And on this order of string, you are calling the set method that takes a string as a parameter. Great. But now it turns out that at runtime, this object is in fact an instance of string order. So what you really want is not that set object method from the order of string to be called, but the set string method from your string order to be called. So you have this inheritance problem there. So what is really happening is that the Java virtual machine sees that the set object from the order of string method class is overridden by this hacked synthetic bridge method set object. So it's going to call that method instead of the method from the order of string. And you can see here the bytecode of this method. It will first check if the parameter is really a string. And if it's not, you'll have a class cast exception. And if it's a string, you can see that there is an invoke virtual set string. So it will redirect the call to the proper set string method. So this is how this synthetic hack is working really. But we are not quite done with it, because there's another hack to be done if you want this kind of ugly stuff to work, which is the other one. And now it turns out that we have, in Java, there is the world of the compiler, and there is the world of the JVM. And it turns out that sometimes the JVM and the compiler do not really work exactly the same. For instance, in the signature in the world of the compiler is just the name of the method plus the parameter. The return type is not taken into account. So it means that if you want to overload a method, you cannot have two different return types. You can have a different set of parameters, but that's it. But it's not the case for the JVM. For the JVM, the signature holds the return type of the method. So you can have two methods with different return type. And it turns out that here it's the case once more, because I have this method called get that returns a string in the string order class, and the extended class, which is the order of string, just have a get method with an object as a return type, which is obviously not the same. But the overridden of those two methods will work with the same kind of hack, just because it has to work in that way. You want the second method, the get method from the string order, to override the other one. So those are the kind of hacks that were needed to be implemented in the language, both in the compiler and in the JVM, to be able to make those generic work. We just talked about arrays, Maurice, and it turns out that with arrays, we have one more category of problems and hacks to be made, is that if you want to tell an array of order of string from an array of order of integers, well, you can't, because in the class file, what you see is an array of orders, right? And if you have an array of two arrays of orders pointing to the same memory place in your JVM, you don't have any more information to throw this ugly array store exception. So it's not possible to tell an array of integer from an array of string. So if you want this array store exception to be thrown, then you cannot really do that. So the decision that has been taken is in fact that arrays of generics are not allowed in Java, and we all know that. If you try to do it, then you'll have a warning also telling you that, yeah, this cannot be enforced by the compiler, in fact.
The basic problem is that the type scheme that was devised for Java for arrays in 1.0 was just going to always be incompatible with proper generification. And we just have to live with the consequences of that.
Yeah, absolutely. And how about lists? Well, it turns out that we have the same kind of problem with lists, the problem you saw with covariance and on arrays, right? We know that list of integer cannot be a subtype of list of numbers, how odd this may look. But then it turns out that you cannot have this code to work.
This is just the same code. If
Yeah.
you made lists covariant, you'd have exactly the same problem as we had with arrays.
And what was possible at compile time with arrays was made not possible at compile time with lists. for some reason. Right. But then it turns out that if you want overloading here with the sort method, if you do not have this extension mechanism between a list of number and list of integers, it means that you will need to have a sort method for any type of list you have, right? List of number, list of integers, list of string, etc. What you really want is to be able to sort a list of comparable objects, for instance, or maybe just object and pass the comparator as a second parameter. So to get rid of this, another very nice feature of the generics that makes the fortune of every kind of generic book writer or trainer.
You have to introduce covariance somehow, right? We've seen that the collections themselves can't be covariant because of the problem that we saw with arrays, but somehow they had to reintroduce covariance. It happens with every language. It's not only Java.
I agree.
Java's solution is kind of idiosyncratic. It's kind of a bit strange, but everybody gets this problem.
So they invented something that everybody understands so well, which is called wildcards in the generic type system. So you may have a list of objects that extends numbers, and then that list can be extended with list of numbers, list of integers, list of floats, doubles, etc. And you name it. So now you can have a sort method made overloadable. I don't know if overloadable in the form of a list of something that extends number.
And that wildcard query extends number indicates some fixed but unknown subtype of number. It could be number itself, or it could be any subtype of number, and that's how covariance gets back in on this occasion. And we can use in this case, covariance works here because the sort method is only taking things out of the collection and not putting them back in.
But if you check the implementation of the sort method, you will see that at some point you will need to put the data back inside the list, and there where you have a cast and another hack. And
internally, the sort method will have to be type unsafe, but at least it's hidden in the library. You don't need to be type unsafe when you're writing client code. So you can see what a lot of problems Java had with implementing generics. Mainly, more than anything else, the two big problems were no runtime type information, this type scheme for arrays, which suited Java 1 but didn't suit Java 5. So how about Scala then? Well, generics in Scala was free of constraints, free of the Java constraints, except for the fact that it was still going to run on the Java virtual machine. So one of those problems still remained, no runtime type information. So they still had to use, they were tied to erasure, and they still use erasure. But they could at least define arrays on top of a new collections library, and they didn't have to suffer the horrors that the covariant type scheme for arrays introduced. And now they had something new that they could do, something better than anything that Java has, because they were starting from scratch with a completely new collections library, so they could actually define their structures according to what use you expected to make of them. Well, immutability, everyone knows now, immutability is good. Right? We're supposed to be using immutability wherever we can in our code. So actually to have immutable data structures fits very nicely with this idea that covariant data structures are ones in which you want to be able to take things out. So in the box of code there, you can see we've got a class pair here, which is immutable. And so that plus sign on the type says this type will only ever be used covariantly. Because we're only ever going to be able to take things out of a pair, it means that a pair of integer really can be, safely, a subtype of a pair of number. And what that means is that you actually get it means that the client code can look a lot better. So there we can define pair of any val. We've defined a method toString on a pair of any val in Scala, and we haven't had to use a wildcard or anything like a wildcard at all. We've shifted the covariance from the call site to the declaration site for pair. And if you compare that with what you'd have to write in Java, you can see the differences. I've written something very similar there. And you can see that the toString method there, it's a deliberate misspelling, so it doesn't clash with the object toString. You can see that that we've had to use variance at the definition of the toString method there, and that means every time you write a client method that uses a library class that you need to define the variance, you need to grapple with the wildcards. So you've got to think about it. As against the Scala declaration site technique, which means that the library writers have to deal with it. And anybody who's looked at the signature of the methods in the Java util collections, those static methods there, the signatures are just quite difficult. They're really challenging because there's an awful lot of angle brackets there, and there's an awful lot of query extends and query super. They're pretty tough going. And on the Scala version, they managed to make them look very, very much simpler. So declaration site variance, which Scala has, is really a big improvement. And I think there's some talk, or there's a JEP out there, an improvement document.
Precisely for what you mentioned about
for introducing declaration site variance to Java. But they would need to have, it's only going to work with structures that you know what they're going to be used for, whether they're going to be immutable or they're not going to be immutable. So that is a kind of quick run through of the story with generics. I mean, that's part one. Part two and part three, which are about closures and about pattern matching, aren't such hard work because the constraints on what Java could do aren't so severe. Generics was the feature that got bent out of shape the most. So closures, higher order functions. What did Pizza do about that? Well, the problem was that the Java type system here didn't have function types. Functional languages have function types, have functions as first-class citizens. They're as important to the language as variables are, or in Java as classes and objects are. But Java doesn't have a concept of functions, and generally speaking, object-oriented languages don't. Scala did because they wanted to get away from this. So the pizza writers came up with a quite nice solution, which has actually been the solution that everybody who works on the JVM has adopted since. Java, Scala, everybody else. For each function, they said we're going to create an abstract class with an apply method. It's variants of this solution have always been the ones that have been used. And that's how you fit functions into the object scheme. Still, we don't need to define functions as some very separate thing. And this is how lambdas are in Java, of course. You know that a lambda fits nicely into the Java type system because it's just an implementation of an interface. We already had those. The big question that I think they had to face was capturing non-final local variables. So there was a huge debate in Java when lambdas were introduced, like, are we or aren't we going to capture non-final local variables? So JavaScript programmers think that Java lambdas just aren't closures at all. They're not the real thing. They're not even higher order functions because they can't capture them. And so the pizza paper is pretty non-committal about this. I think they sat on the fence for it. So that's really the story of pizza. The higher order functions, they knew they had to have them. They've been in functional programming since forever. They're like the essence, really, of functional programming. And what does our code show here? Oh, I know. Yes, the second argument to max there. It's a kind of pseudocode. This. It's not really one thing or the other. But the second argument there is a function from S and S from two types to Boolean, and obviously it's meant to be a way of comparing two types, and it's going to say whether or not the first one is greater than or equal to the second one. And so you can use that function. If you've got a list of S, you can take the function and apply that function to every pair of values in the list, and you'll get the highest value in the list. So this is an example of a way in which a function can be a parameter to another function. So lambdas in Java, when they finally arrived after a huge argument over what they should look like in 2006, was eventually resolved in favor of a very similar scheme to the one that was in Pizza. Instead of defining an abstract class, we use something called a functional interface. It's an interface instead of an abstract class, but the basic idea is the same. It must have only one single abstract method, a single abstract method, and then that allows it to fit very nicely into the Java type system. So it's really very, very smooth, I think. They made a decision about the capture of non-final local variables. They said, we're not going to do it. We're not going to do it. And part of the reason for that was that the main designer of the lead of the Lambda implementation team was Brian Getz. And a few years previously, he'd written Java concurrency in practice, and he was really up on concurrency. And he's saying to himself, I'm sure this is it. I haven't asked him about this, but I'm sure this is the case. He's saying to himself, we've got all these rules to make sure that a field in a Java class is, if it's concurrently accessed by different threads, every access to it must always be guarded by a monitor. And that's quite a simple rule, and we've learned it, and we're good with it. Now, if we start applying that to local variables as well, nobody's going to know where they are. So the decision was, we're not going to allow it.
They don't have this problem in JavaScript.
Pardon?
They don't have this problem in JavaScript.
Well, they don't have this problem in JavaScript because they don't have multi-thread programming in effect. Yeah, that's actually it. In Scala, they were able to very smoothly adopt the idea of functions. They're actually implemented under the hood with an exactly similar scheme to the one there is in Java, but the type scheme. The type system of the language actually has functions as first-class citizens. It looks like a real functional language. Under the hood, the implementation's the same, but the type system's much better. But they made the decision that in Scala they would be willing to capture local variables. How does that work with concurrency?
Well,
it doesn't. You have to do the work, and now you have to double your precautions, because now every local variable is potentially, if a lambda or a closure in Scala, it's not a lambda, it's the full thing. If it can capture a local variable, then it can continue to reference that local variable after the method that declared it has gone away. So the local variable or the block it's in has gone away. So now you have to worry forever that lambda might be executed on some other thread, and you could get concurrent access to local variables, which is a no-no in Java. And so the result of that is now you're going to have to guard all your local variables that are under concurrent access by saying they've got to be, they have to be guarded by the same monitor. Yeah, not very keen on that, actually.
You don't want to do that.
No, you don't want to do that. So another feature that's quite interesting for the use of higher order functions in both Scala and Java is partial application. So this is really important to functional programmers. The idea of partial application is that you can take a function on more than one parameter and you can apply it to just one of those parameters. And then it's like the function's sort of half applied and it's just waiting to be completed with the other half. So we're defining, in this code, we're defining a partial application function. It takes a function on two parameters and applies it to, in this case, it's a function on two strings, and it's going to be doing, I think, you imagine it's like doing index of or something like that, yeah. And it's applying it to the first one, so it's ready for the second one. So the s arrow by of word of s is a function on a single string. And you can see at the bottom there that we're applying by to index of, and then finally we get an f which is on a single string, and it will look for it'll search for the substring in hello. So it's kind of primed to go on hello. You can do that actually much more simply in Scala without all of this fuss. If you just define the parameters to a function, like in the first line of the bottom box, as two separate parameter lists, then you can just say, I want to apply, as like on the right-hand side of the second line, you're saying, I'm going to apply it to the arguments in the first parameter list. And then I'll be ready to go when I get given the second, when I get given another string to search for. So that's partial application of Scala, and it turns out to be really useful. And actually, what we hadn't noticed, but we should give a shout out here to Rémi Forax. Did I get that right?
Yes, I think you are.
Rémi Forax, who is a colleague of José and helped us a lot with the preparation of this talk, who pointed out that something very similar actually is happening in Java when you have a bound method reference. Are you supposed to be talking about this? I think you are. You should have interrupted me.
Oh, no, sorry. I never interrupt you.
You always interrupt. Get on with it. Get on. We're running out of time.
So yes, this is just an example of partial application. In Java, we don't have this very nice syntax that has been created in Scala to tell that the function, in fact, takes two parameters that are completely separated, and that they can take that function to create another function, take that B function to create another function by just fixing one of the two parameters. But we have some kind of syntax that looks like this in Java, which is called the method reference, the bound method reference in this example. And here you have a nice example of it when you are looking for a specific string of characters in another string of characters.
So the bottom box there is exactly corresponds to the bottom box that we had on the previous slide. And if you're wondering, a lot of people are very confused about method references and why we have this nomenclature for them, bound and unbound method references. And the reason is because this is a bound method reference because the receiver here, the thing that the object that the method is going to be called on is always the same for a bound method reference. Here, the object is the string hello. And the alternative, of course, is to have the literally big S string double colon hello. And that's an unbound method reference because it needs the receiver as well as the argument that the method's going to be passed to. Here, the receiver is fixed. Whatever you call this with, it's always going to call index of on the hello object.
Absolutely. All right, and that's it for lambdas and closures. Last part of this presentation is about pattern matching. Now, pattern matching, if you're just familiar with the Java language, you may have never heard about that. This is going probably to change a little bit in the next years to come, I would say, because pattern matching is going to be introduced in Java, and we're going to show you examples of that. First thing, pattern matching was already defined in the so-called pizza papers that we just show you. And this is an example of code. You have a class that is a class of vehicle. And this class has two extensions. Now, this is a syntax to express what is called a sealed type. That is, you create a type, which is could be an abstract type, which is called the vehicle type. And you create two extensions for this type, and those two extensions are just fixed, right? You cannot have any more extension to these vehicle types. The sealed types, we are going to have them in Java also, so I'm going to show you the syntax to build that. And then we create this factory method, capacity, that takes a vehicle as a parameter. Now, of course, this vehicle can only be a car or a bus, and the compiler knows that, and it's also enforced at runtime, right? So your switch just have two cases, and you don't need the default clause of that switch expression, just because we know that there's no other possibility, right? And you can see that the first case takes a car, and the car is defined with the color in it in some kind of constructor-like representation, syntax. And this color, in fact, it defines the variable color on which this car has been created, and you can use this color directly in the return clause here, just like this. So if the color is red, then the capacity of the car will be 20, because it's a car for ants, I guess. And if it's not red, then it's not a car for ants, it's a car for regular humans. So the capacity is only 4. And if it's a bus, it's a small bus, because you can only put 12 people in it. It's a VIP bus, right? So in Scala, the syntax is the following. You also have the seal types in Scala, define a vehicle, and the only extension of that are just the class car and the object bus. So the object bus is a singleton in Scala, define a singleton. Yeah. That are both extensions of the vehicle class. And you can define this capacity, and you see that here you still have a switch, which is not a switch anymore, it's a match, so because it comes from pattern matching precisely. But you have a similar syntax than the one in pizza. That is, if you have a car that has been created on this color variable, Then you can deconstruct the car. This is what is called deconstruction, to get the color field out of that car, and tell that the capacity of the red car is also 20, and the capacity of other cars is 4, and the same for buses. You know that you have here a syntax that kind of look like the syntax of lambda expressions, but it's not a lambda. It's really a switch-like expression. And in Java, this is what we're going to have, Maurice.
Yeah. Real soon now.
Yeah, real soon. Very I mean, really soon. Okay. The syntax is probably not fixed yet, so don't do any kind of money spending decision on this kind of syntax, as usual, even if we don't work for Oracle. So we will have CIL types in Java that can be defined for classes, abstract classes, or interfaces. So here it's a sealed interface. So the compiler knows that this interface can only be implemented with the car class and the bus class. Note that the car class is not really a class, it's a record, and the record is built on a set of fields. Here, only a color, but you could have other fields on it. The nice thing is that the class is automatically created by the compiler with the getter, no setters, because the class is final and it's immutable. The toString, the equals, the hash code, everything. So bye-bye Lombok and this kind of ugly things that you may be using in your Java code. And you can pass this CIL type also to a switch. And here, the pattern matching gives you the possibility to do roughly the same thing as in Pizza or Java. That is, say that this car has been built on a color, and then you can do this, and that with the car itself and the color also. Note there is one little more thing that you can do, is to precise that if this car has been built on a color that is the color red, then you can directly, it's the next slide, sorry. If this car has been created on a color that is red, then you can directly return 20, so you don't have this ternary operator.
So we're going to do.
We all love.
So we're going to do better than Scala does.
Well, it seems that we're going to do better than the Scala does. And plus, the CIL type is really enforced both at compile time and also at runtime. Yeah. Even if you're using some kind of agent or some kind of reflection of hacking, backdoors, everything, any kind of thing, you cannot create more types than the one that have been declared there to implement the CIL type defined there.
Come on, we're keeping these people from their coffee.
Oh, sorry. We don't want to do that.
So that's the story. As you can see, the main part of the story is, wow, what we've had to do, really different approaches that Java and Scala have taken. My first conclusion from this is, wow, language design is really complicated. Any language designer could have told me that, and they did tell me that. Right now, I'm actually living with one of those people, unfortunately for me. And yeah, he's often told me that language design is really complicated. But backwards compatibility makes it way more complicated. So that's why Java's been so slow to adopt these things. And Java's always had placed this really high value on backward compatibility. It's only now that we're seeing a point at which code from 1998 won't reliably run 20 years later. That's going to start to happen, but it's taken a really long time for them to yield even to that point. Scala had a completely different attitude. They don't care, frankly, they don't care that much about backward compatibility. And I think that means that in the end, they'll probably end up with a much better language in the end, but they'll have lost a lot of people along the way because it's difficult to invest in something where you are going to, for every revision of the language, you're going to have to make changes to your code base. And if you've got a big code base, that's a pretty high price to pay. So both viewpoints have their advantage. Scala's actually shown what you can do if you start from a relatively greenfield, what we call, so a relatively clear situation. But Java, well, they're very, very much more cautious. This man is the epitome, the very essence of cautiousness. He says, and he's the man who's in charge right now. He says we don't want to be the first to include a feature because every feature we add will never be removed. That's actually when Java has, I don't know how many millions of programmers are supposed to be around the world.
12 is the last figure that was
and it's it's still the number 1 language in the TOB index. That tells you you've got to really think very, 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 very hard before you add anything at all. So that's exactly what Brian does for years on end. And then we get something that I think in the case of Lambdas that looks like it really will stand the test of time.
And it still doesn't prevent the language from evolving and taking these new features in.
Yeah. Okay,
well,
so that's us.
Absolutely.
Thank you very much for your attention.